was recommended that I make a video with the solutions for this last Desmos activity. So let's hop into it. Why are you not scrolling? Oh well. Put these graphs into pairs so that one shows the derivative of the other. All right, so there's some things that we could look to just always match slope, okay? But if you do that, it's very inefficient. So I can look at something here and I can ask, well, which one matches the slope? And you'd have to go through every single one and kind of like rule them all out. What I would like us to get used to is a combination of matching slope and remembering that derivatives tend to keep similar functions in similar classes. So for example, when I look at this, I see an exponential function that's decaying. And so we should think of something like e to the negative x. And when you do that, actually, hold on, now I'm like pausing and thinking, wait, did I get this right? Oh, it's kind of more like a 1 over x kind of thing. So with 1 over x, it's the derivative of natural log. So I'm expecting that the top function is the original and the bottom function is the derivative. And let's see if it makes sense. So in the original function, I should begin with a very steep positive slope. And I know that because the derivative function has a very high positive y value when I'm beginning, meaning when I begin on the left side of this graph. So I'm near 0, but I'm in the positives. And then as I move to the right, my slope stays positive, but it gets less and less big. Similarly, as I move to the right, my y value stays positive, but it gets less and less big. So, okay, these two are paired together. And that's sort of the one exception where natural log switches to be 1 over x. But some other things that we should look for, we should go, oh, well, this kind of looks like a trig function, and this kind of looks like a trig function. So they should be paired together, and the question is, who is whose derivative? But at the end of the day, it doesn't really matter because it just says put them in pairs, so we know we should put these two in pairs. But, okay, who is whose derivative? Well, just check a few points. So if I look at this bottom graph here, it has a positive slope at 0. And this graph here has a positive y value at 0. So I'm thinking it could be the derivative. And as I move in the original graph to the right from 0, my slope, it's positive, but it gets closer and closer to 0 until I hit the peak. Here, my y values are positive, but get closer and closer to 0, which would correspond to the peak of the below graph. So in fact, in this case, the top derivative is the graph of the bottom, but those two get paired. All right, a function like this is kind of like an x cubed, so we should expect its derivative to be something like an x squared. It should be some kind of parabola. So here's one parabola, and we only have the one option, but those don't go together. Maybe I'm missing a tile. Maybe it's because, for whatever reason, this is not scrolling down for me. Ah, here it is. It got paired together. There we go. Okay, so this is what I mean by similar functions. So the derivative of a polynomial is a polynomial. So the red curve looks like an x cubed. And so I should expect its derivative to look kind of like an x squared. And then after that, so that helps me narrow it down to these two parabolas, one red and one blue. And then I just start to match critical points and slopes. And so the blue parabola, it has a y value of 0 around the same spot where the red x cubed graph has a horizontal tangent line. And I'm always in the red graph going uphill. So in the blue graph, my y values are always positive because the y value of the derivative tells you the slope of the original. Okay, so what else? Derivatives tend to jump. So in this case, my graph that has an erratic slope corresponds to the derivative of this very discontinuous graph up above. And you can just kind of check the green line segment of the original graph is a constant negative slope, and that corresponds to a constant negative y value in the derivative. Then we jump to a constant positive y value and a constant positive slope. Then there's this little increasing curved red section on the original. That's sort of just after x equals 0. And that curved section corresponds to a slope that is getting steeper and steeper positive. So that's the blue line in the derivative. So anyway, you can just sort of go through and check those. So let's put that off here. All right, the derivative of x squared, that's 2x. And again, we see the derivative of a polynomial is a polynomial. In this case, a degree 2, aka a quadratic, becomes a degree 1, aka a line. So those two are paired up. And then derivatives of exponentials are exponentials. And so this is something like e to the x is e to the x. And so sure enough, these two are paired together. Okay. All right, sketch the derivative of the function shown below. All right, so whenever I'm sketching derivatives, I want to put down dashed lines where critical points occur. This is not necessary, but it helps me to do it because it breaks up what's originally a very hard problem, or at least a more complicated problem, into a bunch of much more manageable pieces. So, critical points, in this case, have to do with when the slope is 0 on the red graph. And the y values I'm going to put down for the derivative correspond to the slope of the red graph. So in other words, when x is 0, my slope is 0. So I put a little dot there. And when x is like 2.5, I also have a slope of 0, so I put a little dot there. These two graphed points, they correspond to points that lie on my derivative graph. Okay, so what else can I say? Well, I begin and I'm going uphill, which means I begin with a positive slope. So if I was to graph the derivative, I have to begin with positive y values. And my positive slope is less and less positive toward the end. In fact, it looks like it approaches a 0 slope. So we could just do a straight line down to that point there. And there's no way to say who's right or wrong because our eyes are just not that great at this level of detail. You could, when you look at this, we'll go in red, you could say, well, it seems like I'm very steep all the way up until like maybe here, and then I drastically get less steep. And if that's the case and you want to represent that, then what you should do is stay up at high y values and then drastically come back down to 0. So both of these blue curves are valid guesses at a derivative. So y equals f prime of x. And anything in between, those are all valid. You could even argue that this one's valid here. In fact, right, this looks like an x cubed. So knowing that it looks like an x cubed, you could just jump straight to saying, oh, well, I bet my derivative is going to be something like an x squared. And in fact, it will, to some extent, have this shape. Okay, and the point I'm trying to make is we can't really pin it down exactly, but we could, for example, just do a straight line here, and we could just, oh, my pin's kind of acting up. I could just get a bunch of little straight lines as long as here, negative y values correspond to negative slopes on the red curve. Positive y values correspond to positive slopes on the red curve. And this is why I like to put down markers at the critical points, because then I can just focus on one section. I can say, okay, in this region, wow, the pin is, okay. In this region, I had better always have positive y values for my derivative. So I always have positive y values for my derivative. Then in this region, I'd always have negative, so I always have negative. And then I always have positive. And there are other things we can do to kind of help out. So for example, we could say it looks like this spot right here is the most negative. And so then you should make that correspond to the lowest y value on the derivative. Anyway, any solution that kind of looks like this green curve, totally allowed. All right, match the best derivative option with the original function that's shown in black. All right, so right off the bat, what are some things we could do? We can look for critical points. So I should expect to have a derivative with zeros at x equals 0 and a little bit after the first vertical line, which looks like it would be 2, 4, 6, 8, 10. So maybe like a 2.7 or something like that. So I need a function which has zeros at 0 and maybe like 2.7. So this seems like a good candidate. And this might be the other candidate. Okay, so let's get rid of the ones that aren't good. All right, now the question is who's who? And so we just look, well, the black curve begins with increasing, and that means the red curve should begin with positive y values. So this is the one that begins with positive y values. When I say begin, I mean just scan from left to right, and where do you sort of begin? Whereas here, my y values begin in the negative, so I know it's not you, and in fact, it's you. All right, sketch a derivative. So I'm going to begin with giving myself markers of the critical points. Okay, there's one, here's another critical point, and here's another critical point. Now, last time, when I went to plot the derivative function, I put down dots here because last time it looked like the slope at the critical points were 0. This time that's not true. This time every critical point actually is going to correspond to a jump in our derivative. So, in other words, there's going to be open circles on these lines. All right, so what happens with the derivative? Well, if we look at the original function, I have a positive slope, and it looks like I kind of approach 0. So if I want to graph a derivative, I had better begin with positive y values, and I had better approach 0. You might think it looks like your slope is a little above 0 here, and that's fine. You can put an open circle up here. Wherever it looks to you like this slope is approaching, that's the y value I want to approach. So to me, it looks like it approaches basically 0. And so I'm just going to do a straight line that starts out positive and approaches 0, because these y values correspond to the slopes that have the same x-axis. Right? So right here, I have a small y value, and I have a more shallow slope. Okay. All right, so we've now taken care of that section of the derivative curve. So now I'm going to look at the next section, and I'm going down with kind of a big positive slope, and it looks like I approach 0. So if I was going to plot this, I would begin with a noticeably positive slope, and I would approach 0. So maybe connect it like that. All right, then in the next section, I have a constant negative slope, and we just have to jump to it and have a constant negative slope. There we go. And finally, in the last section, I have a positive slope that begins really positive, and then it kind of like mellows out, something like that. Okay, so this would be a valid curve. What are some things we're looking for? We're looking for positive y values over here that decrease. They're heading down toward whether it's 0 or 1, but well, arguably not 1, because we want to match the slope coming in from the left here, which is close to 0, right? It might be like 1/10 or something. And in the next section, we look for, okay, we want to begin with a negative slope, and we want to approach a 0 slope, so that's what we do. Okay, let me rephrase, because when I say we begin with a negative slope, that means we begin with a negative y value, because the y value is the slope of the black function. Okay, and that slope goes to 0. And then in this section, we have a constant negative slope, so we would look for a constant negative slope. And finally, we have a big positive slope and a less positive and a less positive, so we just kind of do something like that. Okay. So, more matching. This time, they're really getting this piecewise notion. Okay, so when we begin scanning from left to right on this black curve, the slope is positive, and it looks like it decreases towards 0, right when I get to the peak of that cliff. So I need a red curve that begins with positives and sort of goes down to 0. So this is out because it sort of stopped too high, if I'm looking at this initial red line on the left of this. And this one's out because it begins saying your slope is negative. That's why the y values are negative down here, so that's out. So now it's down to these two. Okay, so after I get to the peak of, it's around -4 of this black curve, then I start to go down, which means my derivative had better jump from being 0 to something negative. And this is the one that jumps. This one doesn't, so it's out. Okay. This card does jump, but it jumps from a 0 to a positive, which means in the black curve, if I were to match this, I'd have to go uphill even more. And this is going downhill. So anyway, this is out. All right. With things like this, look for a critical point and see what happens. See if you can get some consistency here. So, for example, the gray curve that I just highlighted with all the dots, it looks like it has a critical point at 0. And if we're thinking, okay, maybe this gray curve is f, then its derivative curve has to go through 0 at 0. So we have no choice but to make this the derivative curve. Okay. So now I'm thinking, whatever I assign to this curve here, we're sort of forced to where this other one has to be its derivative. If that's the correct assignment. We'll talk about that in a second. And then I'm asking, okay, well, does the derivative of this one appear? Can I get rid of this this point? There we go, great. So does the derivative of this curve appear? Well, at 0, it has a negative slope. So it cannot be u. Oh, but maybe it could be u. Ah, so who is whose derivative? So we just have to check a little further. So if we look at this spot a little bit past 5, this little point here, so it's at 2 pi, it looks again like I have a horizontal tangent line, and it looks again like this curve equals 0 at that spot. So now do I have two matches? Let's see. So, all right, in other words, do both of the horizontal tangent line locations I've looked at for the curve highlighted with all the dots here, let me just, it's not a correct labeling, but let me just say that this was F, for example. Okay, so I'm looking at that curve and I want to see if indeed its derivative is this one, all right? So, well, I look at its horizontal tangent lines, so it happens at x equals 0, and again at x equals 2 pi. And the orange one, yeah, it has a 0 at x equals 0, and again at x equals 2 pi. Okay, do some other things line up? So if I'm looking at this purple curve, it's going uphill between x equals 0 and x equals pi. But if it's going uphill, that means its derivative should be positive. So the orange curve cannot be the derivative of the purple. And let's try it the other way around now. Remember how in the beginning there was sort of this mismatch where we were only looking at x equals 0, and it was sort of like they could be each other's derivative, and it wasn't too clear. So now we're switching roles, and we're going to see what happens. So if the orange curve is the derivative of the purple, after I switch roles, then let's see. So at x equals 0, I had better have a negative y value for the derivative because I have a negative slope, and indeed I do. There we go, negative 1.5. And what else? Let's see. So on the purple curve, it looks like I have a horizontal tangent line at pi. And on the orange curve, I have a 0 y value at pi. So these look like they're matching up a lot better. And in fact, I think it's safe to say the orange curve is the derivative of the purple. But we actually have to go up one more layer because the derivative of the orange is not this last gray curve, which means the last gray curve must have been the starting function. So I'm going to make this the starting function. And, okay, let me move this a little bit. There we go. There's f prime, and here's f double prime. Okay. So before, we figured out that what is now green was the derivative of the orange. Okay. It's just that since the remaining curve was not the derivative of any of them, it must have been the original. And now you can go through and check, and you can make sure that, yeah, like the critical points match up with the zeros, and the general increasing and decreasing structure matches up as well. In general, you just kind of have to take it 2 curves at a time in the beginning and find a relationship between the two, if there is one. If you're not even matching critical points, so like for example, I'm not going to compare the green and the purple because, well, the green cannot be the, okay, I can compare them, but they're not going to be derivatives because the green curve, well, it has a critical point at x equals 0. So if the purple was its derivative, it needs to go through 0 at 0, but it doesn't. And that's the same if you switch roles. The purple curve has a critical point at x equals 0, which means its derivative had better go through 0 at 0, so it can't be the green curve either. So anyway, process of elimination, take it 2 at a time. All right, summarize what you found on how you determine whether or not you have a derivative. So I would say that we match critical points of parent function to y equals 0, which is also known as roots of the derivative. Then you want to check if an original function is increasing, check increasing, is paired with f prime being positive, right? And similarly, decrease being paired with f prime being negative. And you just kind of do that and iterate it. So, all right. So now we just have some derivative rules. So I have complete faith that you can compute the derivative of this. It's just the power rule. Bring that 2 down. You get 6 over 5x. So we have 6 over 5x. All right, and if we launch this ball, then it's going to kill all those stars. And here we just have more power rule, and I have complete faith that you can do that. Okay, now we get to something a little bit more tricky. So now I just want to show you a resource that you can use when you're kind of stumped and you just really want to be able to just check your answer quickly. So, oh, actually I already had it here, Wolfram Alpha. Okay, so Wolfram Alpha, you can see that URL at the top. I can ask it to compute the derivative of, and that function was 2x times sine of 1/2 x, but I'm just going to write it as x over 2. Okay. And it thinks, and here you go. So the derivative, we can see it right here in the first line. It's 2 sine of x over 2 plus x times cosine of x over 2. Okay, so I know these are going to get a little bit trickier, so let me actually see, oh, that's right, it's just Desmos. Let me see if there's a different one that I want to do as an example. All right, I'll do this one as an example, and then we're going to call that for the video. But by the way, again, you can just enter this in Wolfram, and it'll tell you the answer. But let me just go ahead and work it through really quick. So we have 3x squared sine x over e to the x. Okay, so 3x squared sine x over e to the x. Okay, so I want to take the derivative. And one thing is my brain sees this division here, and I'm thinking, okay, there's going to be a quotient rule. And the function on the top is this whole monster. And in order to compute the derivative of what's on top, I had better use a product rule. Okay, so let's just take this in steps. So my top function is 3x squared sine x, and its derivative requires a product rule. So I'm going to take the derivative of this first function, which is 6x, and I multiply it by the second. Plus, and now I take the derivative of the second function, which is cosine x, and I multiply it by the first, 3x squared. Okay, and so that's for just the top. Just my bottom function, just called g of x, is e to the x. Well, this is kind of nice because its derivative is just itself. It's just e to the x. Okay, and now I have all the things I need to do the quotient rule, which is low d high minus high d low over low squared, if that's how you remember it. But okay, so let's go ahead and do it. So I'm going to take the derivative. Notice I did not put an equal sign here. I put an arrow because if I write something like, let me do what's wrong. Okay, so this right here, this is not true. Okay, but if I write this is equal to, and now let me do the quotient rule. So I take the derivative of the top. That's this whole monster. So let's see. I have 6x sine x plus, and I'm going to put the 3x squared in front just because it looks a little nicer. Okay, so this times the bottom, e to the x, minus the derivative of the bottom times the top, 3x squared sine x, all over the bottom squared. Okay, this is a really common thing that we get on exams and quizzes, and it's just not true. Okay, these two functions are not equal. That is a lie. What is true is the derivative of this function is in fact equal to this function, right? So if you're going to write an equal sign, you had better write the derivative operator. And if you don't want to write that derivative operator, don't write an equal sign. Just put a little arrow. You could, just put a little d up there to let us know you're going to take a derivative or something. But, the thing that's written here and the thing that's written here are just not equal. They're not. But if you include the derivative in the whole, then they're equal. Okay. So anyway, this would be what I would want to enter into Desmos. But I'm not going to do it. That's just a typing exercise. And all the rest of these, I would encourage you, just check them in Wolfram. I don't have anything really magical to say about them. You just got to take your time peeling through all the layers of the derivative rules. All right, see you next time.